All right, so now we're in the 9th lecture, and we're going to put what we've introduced about the crystal structures and the real space and reciprocal space to use today as we look at some very important class of experiments. Together they're called scattering experiments, but in particular we're going to look at X-ray diffraction. So these experiments are extremely useful, especially for figuring out the crystal structures and of crystals and even more complex things like biological molecules. Maybe you all familiar with the example of the DNA. The structure of the DNA, the double helix, was figured out from an X-ray diffraction experiment by Rosalind Franklin and Watson and Crick. So also in biological applications, now a lot of the complex polymers that are inside our bodies and in the bodies of living things are being crystallized into periodic structures. And then by studying their X-ray diffraction spectra, people figure out how are the molecules composed. So even complex polymers which have hundreds of thousands of atoms can be figured out by these powerful techniques. But we are going to look at, we're going to look at even more atoms, but a single unit cell that we're going to look at today will be of the type of the variety that we already looked at before, the FCC, the BCC, the simple cubic, maybe with a basis, so some extra atoms inside. All of these experiments involve shining a wave onto a crystal and then detecting the scattered wave. So then you always have an incoming wave, which is e to the I k r with its own wave vector k, and the scattered wave in principle at a different angle with a wave vector k prime. Now, first, some very general considerations. For diffraction, it is always good to pick a wavelength that matches the periodicity of the object that you are going to diffract off of. So if you remember a little bit about diffraction or interference experiments that you may have had in physics 1 and 2, we were using optical light, laser light, to produce diffraction patterns. And if we use the slits to do single slit diffraction or double slit experiments, or if we use the periodic diffraction lattice, the periods of those lattices and the dimensions of those slits were comparable to the wavelength of light. So hundreds of nanometers. Now, atoms in a crystal structure are quite a bit denser. They are on the angstrom scale. A few angstroms is a typical spacing in a crystal lattice. The periodicity of the crystal lattice is a few angstroms. And therefore, we need waves that are much, much shorter. So if we're talking about optical waves, that would be X-rays. So X-rays are much shorter than visible light. They are just in the right range of a few angstroms. And then you can work out what the energy of these X-rays is supposed to be by taking E equal to hc divided by lambda. So you know the wavelength that you're aiming for. Then it's pretty easy to figure out what the energy is, and the energy turns out to be a few kilo electron volts. So you need these X-rays to have the energy of kilo electron volts, and then they will have just the right wavelength to diffract off of atoms in a crystal structure. X-rays typically interact with electrons inside the crystal. So not with nuclei. We have neutrons for that. Maybe we will touch upon neutrons at the end if we have time. Otherwise, your textbook has a very nice lead into X-ray based on neutrons, because mathematically neutrons are simpler. Neutrons just diffract off of the nuclei, which are very sharp functions, which are very small objects. So it's a function which has very sharp peaks at the positions of nuclei and nothing in between. And then the electron clouds are a bit more spread out in between the nuclei. Electrons' shells have some dimension. But still, it gives a very good diffraction pictures. So these are the three kinds of waves that we use in the lab to do diffraction experiments. And like I said, we are going to be focused on X-rays, 1 angstrom wavelength, kilo electron volt energy, maybe 10 kilo electron volt, interacts with electrons. And X-rays do go deep inside the crystal, can go all the way through. And come out on the other side of the crystal, depending on the crystal. As you know from X-ray images that can be taken of your body, they can penetrate pretty deep, right? The X-rays. They can be stopped by things like perhaps lead, some certain materials. Neutrons, actually, because they have a very large mass, if you work out the energy that you need for the de Broglie wavelength of 1 angstrom, that is a tiny, tiny energy. So milli-electron volts, tens of milli-electron volts as opposed to kilo-electron volts. Right? It's a huge energy difference. And electrons fall somewhere in between with 100 electron volts because the electron mass is 2,000 times lighter than the mass of a neutron. So the wavelength of an electron, to get the same wavelength, you're going to need much more energy for the neutron. Now, electrons are not very penetrating because they interact with the electrons that are inside the crystal, and they scatter very rapidly. So electrons are especially useful for doing diffraction for studying surfaces. So there is a lot of interesting things that are not the same as in the bulk happening on the surface. This is the entire surface science. Is a huge and mature field of material science, physics, chemistry. It's a mixture, and it's a very powerful technique to look at electrons in that case. For example, electron diffraction can show you how a crystal grows one crystal plane at a time by showing the interference patterns in a electron diffraction measurement. So these kind of electron diffraction detectors, you would find them on a molecular beam epitaxy machine that grows crystals plane by plane. So mostly X-rays today, though. Okay, and then just as a refresher and also to explain how this all works, it works the same way as with a diffraction lattice. If you remember diffraction lattice and Bragg formula from your basic physics, this is essentially what happens. So you have these periodic arrangements of atoms, and these are the lattice planes. Right? And what you need to think about is an incoming wave with a wave vector k reflecting off of the entire plane of atoms in this case. So one atomic plane will be a mirror, a reflector for this wave, but then the wave can also partially go through and reflect off of the next lattice plane. Right? And so you will have interferences between the waves that went through and the wave that bounced off the first lattice plane. And you know the interference between these two can be destructive or constructive, and that depends on the difference in the optical path that the two waves have traveled. And so you want to figure that out. You make a little approximation, and you say that, well, this difference is actually just this distance here. And to find this, you take d, the spacing between the two lattice planes, times sine theta and times 2. So one of these is d sine theta, and you have the optical path difference of twice that between the two waves. So that's difference in phase, and if that is an integer number of wavelength, you get this Bragg condition. And so what this Bragg condition tells you is that for certain angles of incidence and reflection, there will be constructive interference. So you will have a large amplitude of the wave in those directions. And for other ones, you will have just nothing, because this is, of course, a periodic structure of lattice planes, which you have thousands and millions of planes. And so if you're slightly off of this condition, there will be destructive interference between these different planes. So you have to be spot on this condition, and that's the Bragg law. So it tells you for which angles you expect diffraction and relates them to this d. Right? So this d would be then the distance between lattice planes. And the distance between lattice planes, you can relate this to crystal structure. We will go through examples of how that works in just a moment. But first, a few general things. Of course, to treat atomic planes which have atoms in them as just planes that reflect waves is an approximation. It gives a very crude, a very useful, but a very crude first cut at what the full X-ray information can give you. And so it doesn't talk really about the intensity of different X-ray peaks that we will see. And so we will use a slightly more complete mathematical analysis. But this is the essence. This is the essence of what is going on. It's this diffraction of the lattice planes. Okay. There is an equivalent approach which takes advantage of things we already learned about the reciprocal lattice, and it is also a very intuitive one. And it's kind of a particle wave duality of these X-rays that gives these two different approaches. So this one is called the von Lauer method or approach. It basically gives the same result, just a different way of looking at it. Here we look at it as really as a scattering problem. So we have a photon with a wave vector k, and it scatters off of an atom at a crystal lattice point position. So here we don't talk about planes, we talk about this just one crystal lattice point, this one atom, and it produces a new wave at the wave vector k prime. So this is a scattering process. Now we have millions of atoms in a lattice. In order to see constructive interference outside of the crystal, we want that the wave that is scattered off of another atom somewhere else in a crystal lattice interferes constructively with the wave from the first atom. So we want there to be a large subset of atoms for which all of these scattering processes give constructive interference. So this atom will be located at a distance t given by a real lattice vector t. So this vector is part of a real lattice because it connects 2 points on a real lattice. And in order to have a constructive interference from these two, it's the same approach as for the figuring out the Bragg law. You figure out the optical path difference traveled by these two waves, and it happens to be these two segments here, and they can be given by k dot t and k prime dot t. So minus k dot t and k prime dot t. So the total difference in optical path is then given by this, and this has to be equal to the integer number of wavelengths. Right? So it's important to know the wavelength of the light that you're shining on your crystal. Now, you can see that this formula is very similar to Bragg's law, because if you take a dot product of two vectors, there will be a cosine or a sine there. So this formula will be the same. We can prove it rigorously, but I refer to your textbook for for seeing that, I will focus on the meaning of this approach, what it gives us. Okay, so k prime minus k is just delta k, and if we look at this formula, we have delta k here, and by absolute value, it is equal to m lambda divided by t, or it's equal in a phase representation. If we divide both parts by lambda, it is just equal to 2 pi m divided by t. And if you remember, that would be the condition, 2 pi m divided by t would give you a reciprocal lattice vector. So the connection between the real lattice and the reciprocal lattice is exactly this. So this is from last week. And so basically what this condition derived here means is that when the difference between k prime and k is a reciprocal lattice vector, then we have constructive interference, and we expect a large intensity of X-ray reflected in that direction. Okay. So when the relationship between k prime and k is a G, which is a reciprocal lattice vector. So the important formula is this tiny blue formulas at the bottom. So this von Laue approach can be rephrased the following way. There must be a conservation of crystal momentum. So remember that if G is defined in the first brilliant zone, so we modulo 2 pi divided by A, then it's called the crystal momentum, and this is conserved. So the scattering between k prime and k gives out crystal, should be related by a crystal momentum vector. So this is if you want, looking at X-rays as particles that bounce off of atoms and then interfere constructively as waves. Okay. There is a visual way to figure out which crystal planes or lattice points in reciprocal space will give you X-ray resonances for a given k. It's called the Evald sphere construction. Here shown for a simple lattice, which could be a square cubic lattice or could be orthorhombic. Looks like the A and B are not the same here. And this introduces another important concept. So the absolute value of k and k prime should be the same. This is because we are talking about elastic scattering. So X-rays sort of just change direction, but they don't leave any energy in the crystal. And so then we draw the k vector of the appropriate length, the one we used, the X-ray that we used, and make it go into the point 0, 0. And then we draw a circle. This is a two-dimensional view, but you can also do a three-dimensional view. And then whenever this circle overlaps with lattice points, like it is the case here for 4, 1, then we expect for this magnitude of k, there will be an X-ray intensity spot in the direction 4, 1. So this is a reciprocal lattice, which is a simple lattice in this case. It is not a BCC, FCC, hexagonal, trigonal, any of those. But when this sphere overlaps with a site on this lattice, then we can connect the point 0, 0 to this site, and this will be a reciprocal lattice vector. So delta k, the difference between green and red, will be G, will belong to a reciprocal lattice, which is combines all the vectors that connect any 2 points of the reciprocal lattice. And so we expect an X-ray resonance in that direction. we will not look further at this Evald sphere, but actually when I was an undergraduate student, we had to plot these things and figure out that for this material we're going to have the these and these, and you can put more complicated points here rather than just a square. And because of how painful it was, I'm not going to go through this with you now, but I just felt like, this is one thing I know, and so I, for real, did it myself, so I thought I'd show you at least one slide about it. Okay. Now, to make it more visual for you, going back to real space now. This is real space, real atoms, but in 2D and a square, so not sure which atoms that would be, but just in 2 dimensions. These are the different possibilities for, if you imagine this Bragg law, for the crystal plane sets that might give you X-ray diffraction. So a 1-1 set of planes would be connecting atoms like this. Diagonally, 1-0 is parallel. And these are more complicated, 1, 2 bar and 1-5. One thing you can see here is that the larger the indices get, the smaller the spacing is between the planes. So 1-1 or 1-0 is the largest spacing. 1-1 is a little bit smaller. 1-5 look very dense, right? That's, of course, because you have to go from this atom and then skip 5 along this axis before you hit the next atom. So the planes go really, really close together. And so the larger these Miller indices, remember these are called Miller indices, the indices in the reciprocal space that label the crystal planes by the normal to the plane. The larger these indices, the closer seems the spacing. And this is true. So last week we've calculated the spacing between planes, and we have these formulas. So you can see that D, this is something that we can extract from the X-ray data, the spacing between a family of lattice planes that gives a strong X-ray resonance. And it's inversely proportional to H, K, and L in this fashion, H squared, K squared, L squared, where these are the Miller indices of the particular planes. And of course, there is the crystal lattice constant for the material is also here, scaling everything. So this is, of course, only for cubic structures. We can write this formula, obviously. Right? But we limit ourselves here to the cubic structures. So this is why larger Miller indices will give you smaller Ds. And look back to the picture from the previous slide to visualize why that is the case. So the business of interpreting X-ray data is to relate a set of Ds that you might get from the data to these indices HKL and come up with a crystal structure that matches what you've observed. Okay. That's the game. Now, to introduce a bit of math here to have a full discussion with the simple cubic lattice, it is easy. This is just the Miller index stuff that I showed before, but with FCC and BCC and other lattice types, we have to do a little bit more math, and for that I'm going to have to consider a little bit in more detail what happens to a wave as it enters the crystal and scatters. If you remember your diffraction, you may remember also that a process of diffraction basically performs a Fourier transform on the structure that you're diffracting through. So if you remember just a single slit diffraction, right, would give you a pattern which is what's it called? A Fraunhofer diffraction pattern, right? So if you shine a plane wave of light through just a slit like this, you will get on a distant screen, which is, you shine a wave like this, e to the I k r, and on a distant screen you will have a function which looks like this. It's kind of sine x divided by x function, and that's the Fraunhofer diffraction pattern. Well, it is also a Fourier transform of this slit, so a function which is like this would Fourier transform in a reciprocal space into this. So the Fourier transform of a crystal lattice is a reciprocal lattice, as I showed you before. And in the case of X-ray, it is not the crystal lattice, not the set of delta functions that we are transforming, but it's, like I mentioned already, it's the electronic orbitals. X-rays interact with electrons flying around the atoms, so they fill some fraction of space around the atom, the electrons do, and that happens in a periodic fashion. So each atom has a cloud of electrons, and so there is some function n, which is the density of this cloud, which you are diffracting off of, essentially. So this function is not a set of delta functions, but it is a function that's periodic in the crystal lattice. So if I take again my vectors t, which belong to the real lattice, the function will map onto itself if I look at it at a distance r plus t, where t belongs to the real lattice. Right? So this function that we are refracting or diffracting off of is a periodic function in our chosen crystal lattice. Could be a cubic lattice, could be a simple cubic, could be BCC, and so on. And the amplitude of the diffracted wave is related then to a Fourier transform of this function. So that's what I want to say. So much like in the single slit experiment, in this more complicated and periodic function, if we want to know the amplitude, we have to take the Fourier transform. Now, I can also motivate it for you from the quantum mechanics point of view, and sort of in the spirit of the von Lauer approach. So we have photons of wave vector k coming this way, and we have k prime scattering off of some potential here, which is this function. This is the potential off of which we're scattering. So this periodic electron density. And so the intensity of such a process will be proportional to the matrix element between the initial wave, the potential, and the scattered wave. Sorry, IKR. So this is the quantum mechanical approach. It's a matrix element between the incoming wave and the outgoing wave is this potential that is in the crystal. And so if I expand this formula, this will give me an integral over the entire space, dv, and then there will be this function n of r, and these two functions, but this one we have to take the complex conjugate of by the matrix element formula. So it will be e to the I k minus k prime r. And this k minus k prime, we know that it has to belong to G, to the reciprocal lattice. So k minus k prime will be G. Those are the only ones that will give us diffraction peaks for a periodic function. This we have done a little bit with delta functions before, but you can also read in your textbook why this is the case, or just remember the von Lauer condition from the previous slide. And so I have to substitute k minus k prime equal g here, and I will see that the Fourier components of the n functions are given by this function.
Is n an operator?
N is yes, it is a scattering potential. So it is an operator where you just multiply the wave function by the potential, like the potential energy is an operator, but it doesn't do anything special with the wave function, like take a derivative of it, or it is just a sort of a magnitude of the potential. So we will see in a few slides that in fact this n is proportional to the charge of the atom. Okay, so this is sort of from quantum mechanics. Again, not a full mathematical derivation of what the scattering amplitude is, but a sort of motivational math for you guys. Okay, so once again, here's our picture, and scattering vector delta k. And like I said, the scattering amplitude will be proportional to this matrix element, and so it's proportional to this kind of function. So the intensity of scattering in the k prime direction will be proportional to this function. It will probably be a square of this function, actually. The intensity is a square of the matrix element. But we will not really look at the difference between square and non-square today. Okay, so just rewriting this in terms of delta k, and then pulling out these ng components. And this is just basically adding to this the von Lauer condition, basically that only scattering by vectors delta k, when delta k is g, those are the only times when we're going to have diffraction. So this is this part here is obtained from here by substituting n of r with a definition from the previous slide, which is in the basis of g vectors, sum of g and g e to the I g r. So if you plug in this definition for decomposing the n of r function in the basis of the reciprocal lattice as a Fourier transform in the reciprocal lattice basis, you will get from this formula, you will get to this formula. And then you can use, looking at this formula with ng's in it, you can see that we already went through this before, that this integral gives you 1 when g is equal to delta k, and it gives you 0 otherwise, because there will be always a opposite delta k for every positive delta k. And this function will cancel itself. So this is just expressed here. So the math here is not very complicated and very intuitive with the von Lauer condition and the idea that when you diffract, you get a Fourier transform. So we have to take the potential of which we scatter and take a Fourier transform of it. This is basically the message here. Okay. Now, it is convenient to express this scattering amplitude that I didn't really derive but introduced to you in the previous slide as a Fourier transform of the scattering potential in the basis of g vectors. Decompose it into n terms, which are all the same, where n is the number of unit cells in our crystal. Then the meaning of this S, which is called the structure factor, is this is something related to a single unit cell, right? So this would be very useful to find out properties of a single unit cell, where the atoms are in the unit cell, what types of atoms there are they the same, are they different, right? This is the information that we would like to know, and therefore it is convenient to express various data related to a single unit cell parameters like this structure factor. And the structure factor works out to be just the integral, sort of a Fourier transform of the scattering potential, nr, so some electron density related to the positions of the atoms, obviously, in a unit cell, over just the unit cell. So this is the integral over the cell. And then you integrate over the entire space by summing it up n times. So this math is very simple. N of r is a periodic function, so you can just integrate over one unit cell and then sum it up n times, and you'll get the full thing. And this term here is because of the 2 pi over a periodicity that is related to the reciprocal lattice. Just this is what's left of it, basically the same thing. So the Fourier transform over sort of a one unit cell is called the structure factor. And it's called the structure factor because this function will have will look differently for different structures like BCC, FCC, and so on. And this is a very interesting thing that we will look at in some detail today. What are the differences between the different lattice types based on this different structure factor? Okay, so so far we treated this n of r very generally. Now let's imagine that in a unit cell we have several atoms, s atoms, and each atom has some electron cloud around it. So remember, a simple cubic lattice has one atom per unit cell, but if it has a basis, for example, one atom displaced by 1/4 in each direction, a different atom of different type, for example, then it would have 2 atoms per unit cell. It will be a simple cubic with a basis. There might be 2 atoms. For an FCC of all the same atoms, there are 4 atoms per unit cell. So there will be 4 n of j terms here in this formula. And for BCC, it's 2. So this is a very convenient representation. And so just plug in this formula and take it and plug it into the SG, the structure factor for a certain G vector. And the structure factor then becomes a sum over J. So for each atom, you have this kind of an integral. Integral of the density of this, integral of the electron density, integral of mass density, some periodic function integrated over the unit cell and Fourier transformed. Right, so this is just rewriting it in terms of the coordinates with respect to each atom. So whereas here we have R, which are the positions inside the unit cell, but the function Nj is centered around the position of the atom, which is Rj. So if we introduce rho, which is R minus Rj, we will have these Nj of rho functions, which are unique to each atom. So they just describe this one atom and how X-rays interact with this atom. So you can imagine that this function will be the same for all atoms that are the same. So if you have chlorine atoms at these positions, it will each come with its own Nj. And this allows us to separate this equation into 2 parts. So you have S, which is called the structure factor, which has this sum over the positions of the atoms given by RJs. So RJs are the positions of the atoms inside the unit cell. And this integral here is going to be called f of j. And this is, has a name of form factor, atomic form factor. Right? So what do we have in the end? In this formula in the frame at the bottom of the screen, it shows you that the scattering amplitude f, which can be straightforwardly related to the structure factor and just scaled by the volume of the crystal. So the scattering amplitude of X-rays depends on the positions of atoms inside a unit cell. So that's the structure factor. The structure being BCC or FCC or something else will mean that the atoms are located at different positions. And so that's the sum term. And times some amplitudes, the form factors, which come from which kind of atom you have. So if you have atoms of the same type, this will be, to a very good approximation, the same function f describing those atoms. So just for completeness, we are going to look a little bit at what this form factor is. Well, atoms are little balls, right, with electrons flying around them. So this kind of function n of rho most likely going to have a spherical symmetry. And to figure out this integral, you would want to go to the spherical coordinates with phi, theta, and r, the distance to the center. And therefore, in these spherical coordinates, you can just integrate out the angles. However, angles will come into this Fourier transform factor because here you have g dot rho, and that gives you a cosine theta, or the angle between them. However, the other angle, phi, the other spherical angle, just integrates out and gives you this 2 pi. However, and the function itself just has a spherical symmetry. It's a Coulomb potential, so it only depends on r. And so we have to take this kind of an integral, works out to be a function like this. This is now still for an arbitrary spherically symmetric potential, but in fact, if you want to assume something very simple, just a nuclear function, so a charge of z at the positions of the nuclei with delta functions, then this form factor will be just equal to z, strictly equal to z. You just plug it in here, the delta function, and you will see that that's the case. Now, I told you that we are interacting not with nuclei, but with electrons. However, we can still assume that f is approximately z. Okay, so I don't think I will ever ask you to prove it or maybe even estimate z, although not sure about that. But just to have a physical picture in mind, just remember that form factors, grow with the charge of a nucleus, for example. This is not a very exact statement, but it is a qualitative statement. And the meaning of it, of the form factor, is the amount of charge at each atom. It scatters stronger when there is more charge. Scatters X-rays stronger. So this is the point here. Now, what do we do with these form factors? How do we go about them? It looks like a bit abstract formulas. Now I will try to make it more concrete, more specific with specific examples. So first of all, we take a real vector R, which has x, y, z components. This is a vector inside the unit cell, or anyways inside the crystal. And then we have to take this g dot r. And remember, g is HKL, is an HKL vector. Right? So G dot R will give us H times X, K times Y, L times Z for the jth atom. J is the enumerating the atoms inside the unit cell. So J dot R will just be HKL, X, J, Y, J, L, Z, J. And these HKL are related to the scattering direction of the X-rays, right? Because K minus K prime is some kind of G. So then the structure factor is just a sum over all the atoms that we have. Form factors in the front, that's related to which type of atom we have. And then these exponential terms with HKL here. And then the coordinates of the atoms X, Y, Z, coordinates of the jth atom inside the unit cell. Now this is not going anywhere outside the unit cell because we already reduced it. The structure factor talks only about one unit cell. So this is the shape of this function, right? And now we can figure out what this function is specifically for the lattice types that we know, the ones we've considered before, right? Because we know for them the X, the Y, and the Z. Okay, so let's look at the BCC lattice. BCC lattice is a simple cubic lattice, and it has a basis of two atoms. So inside the cubic unit cell, there are two atoms. One is at 0, 0, 0. The other one is at 1, 1, 1 with A over 2. So the one is in the center. The second one is in the center of the cube. That's why it's called the BCC. It's the body-centered cubic lattice. One atom is in the center of the cube. Okay, so these are the reciprocal lattice vectors. Now they're not called HKL in this slide. I apologize. They're called N1, N2, N3. This is, I think, from the Kittel book notation. Let's say, so this is a BCC lattice, which means it's made by the same atoms. Each atom is identical, forming a BCC lattice. So the form factor goes out of the bracket here. And then from the atom which is at 0, 0, 0, we get e to the I of 0, which is 1. So this is the 1 that comes from the atom which is at 0, 0, 0. And this term here comes from the second atom. So remember, we have to take, well, in this notation, we have to take N1, X1, plus N2, X2, plus N3, X3, which will just give us N1 plus N2 plus N3, or H plus K plus L, e to the I pi, H plus K plus L. It's pi because it's A over 2 here. Otherwise, it would be 2 pi. Okay, so what does it mean? It means that this function is 0 when n plus 1, n1 plus n2 plus n3 is odd, and it's 2f when n1 plus n2 plus n3 are even. Those are the possibilities. So these n numbers are only integer. They can only be integer. They're HKL, or n1, n1, n2, n3, corresponding to the reciprocal lattice. And so these are the two possibilities. It's either 0 or 2f. It means that some of the combinations of HKL, meaning some of the families of lattice planes, will not give an X-ray resonance, will give a 0, will be absent. And some of them will give an X-ray resonance. So there are some that are absent, and that's unique information that you can use to deduce the crystal structure. Now, I can also explain this to you, why some of the combinations of indices are absent or not allowed in X-ray scattering, by going back to Bragg's law. So Bragg's law would be the in constructive interference between different lattice planes. So for the BCC lattice, there is essentially an extra lattice plane that goes in between the simple cubic planes and is located at, goes through this atom. And for that reason, you have destructive interference between beam reflecting off of this extra plane and one of the original beams. And so when, say, this beam and this beam interfere constructively, this beam and this beam interfere destructively. And so actually what you're going to have is destructive interference. So there will be no no X-ray in that direction. You can also see it from this formula. So you will get 1 from the first term and -1 from the second term. So there is some kind of cancellation going on in the structure factor. So some of the planes are absent. Okay, for the FCC lattice, a little bit more complicated formula because we have a basis of 4 atoms in the centers of each face of the cube, right? Face-centered cubic lattice, centers of the faces have atoms in them, and therefore the structure factor formula is a little bit more complicated. Still, the form factor is outside because all the atoms, we assume them the same. The first atom gives you 1 because it's at 0, 0, 0. And then the other atoms, because they are at 0, 1, 1, 1, 0, 1, 1, 1, 0, give you these kind of terms. N2 plus N3, and 1 plus N3, and 1 plus N2. So a little bit more complicated, but still a function that we can figure out in a very simple way. So turns out that if and only if all of the Miller indices are either all odd or all even, this is not 0. This is equal to 4f. And any other case, we have 0. So quite a few of the planes will be excluded, right, for the FCC, for the face-centered cubic lattice. Quite a few of the planes will not give diffraction. So this is a summary table. These are the rules that we just derived. So actually, for the simple cubic lattice, and we are back to HKL, so N1, N2, N3, and HKL, it's the same thing. For simple cubic lattice, any combinations of H, K, and L will give you diffraction. But for these other common types, for BCC and FCC, there are these rules. So H plus K plus L equals even for BCC, and H, K, L are either all odd or all even for FCC. So what does it mean for some of the initial lattice, families of lattices with some of the smallest Miller indices? 1, 0, 0 is allowed for simple cubic, but is not allowed. It will not give a diffraction peak for the other types. And this is exactly because there are extra planes in between that give you destructive interference when you look in this direction. Okay, so for simple cubic, all of them are allowed, but for BCC, for example, 1, 1, 0 is allowed because 1 plus 1 plus 0 is an even number. However, they are not all even or all odd, and therefore it is not a true diffraction peak for the FCC type. And it goes on and on following these rules. So there are missing diffraction peaks. Okay, so now closer to experiments. How do you get X-rays? So a couple of ways. There is a cheap and efficient way, and there is a high-tech way, which is very expensive but is needed for some experiments. So this is the cheap and efficient way. You have some kind of a source. In this case, it's a special type of copper. And you have a vacuum chamber, and you have a cathode. So basically a wire with electrons. The electrons come out of the wire, and they hit the target, hit the copper, And then what they do, these electrons, they knock out electrons from the copper from the lower orbitals. So this is the atom of copper. This is the structure of the orbitals, K, L, M, families, the higher orbitals. And say it kicks out, for example, these electrons here at 1s, kicks them out, and then higher electrons fall down, and they emit light as they do that. And so for these specific transitions, turns out that the light that you get is very sharp X-rays. So this is a typical spectrum of such an X-ray tube. You have some background, some kind of a shape, like a whale type shape from the background. So there's some continuous emission, but there are these very sharp and much higher intensity peaks which correspond to these atomic transitions. And so then you just lock onto one of these peaks and you have a cheap and efficient source of X-rays by bombarding this copper target. We have one of these at Pitt across the street in Benedum Hall in the Nano Characterization Center. This is the machine, how it looks. You want to know crystal structure of your sample. You go and bring it, put it there. You put your sample here. And this is the X-ray tube here. There are some special X-ray mirrors. And this part here is the monochromator, so to select a single wavelength. And also, you can scan with this mirror, you can scan the angle, the incident angle, the K vector of the X-rays. And here you have an analyzer and a detector, which is typically a semiconductor detector, detects the scattered X-rays here. So this is a scattering experiment that you can perform with a large number of different samples, as long as there's something crystal about them. Now this is another fancier way to get X-rays using a synchrotron. So this is normally a huge facility. And what you have there is you have electrons flying around a large loop, being accelerated to a pretty high speed. And then you take advantage of relativity, the theory of relativity, because when electrons bend, right, their trajectory is flying at near relativistic speeds, they emit radiation. This is from the theory of relativity. We know this. And so there are some wigglers in this beamline, which are basically magnets. So they produce a magnetic field that makes electrons wiggle like this. And at each wiggle, X-rays come out. So these little red photons come out. And then there is a lot of machinery to monochromize them and direct them in a proper location. And then you, at the end of the day, you have a beam of highly coherent radiation in the X-ray spectrum coming and hitting your sample, which you can put your poor sample here. The intensity tends to be enormously larger than from a single X-ray tube, so orders and orders of magnitude, billions of times larger photon counts, and so this is used for applications where you need a very good signal. Now this is how one of these looks. I spent the summer not working here, but in one of the buildings here doing some nanoscience. But this is in France, in Grenoble, a European synchrotron facility. There is one in Argonne by Chicago, very similar, but without the mountains. So I decided to show this picture. So this is the ring where electrons fly around, and then I suppose one of these buildings here is where you can come and put your sample into the beamline and have it studied. Coincidentally, this building is a neutron facility. So there they make neutrons to do also neutron diffraction. This is also very high tech. The principle is very similar to the X-ray tube. So they take protons and they hit a target, and they kick out neutrons from the target, from the nuclei of the material, and then they monochromate and collimate this beam and make them very coherent. So there is a lot of high-tech machinery here. So these places are typically joint shared facilities. This one is run by the European Union, and everyone can come there and get some beam time to study their samples. You submit a proposal. This is how the American facilities also run, or Canadian, and so on. So this is too expensive to maintain by a single research group or even a single university. It's typically a consortium that runs these things. Okay. So the most obvious method of doing X-ray is to take a crystal and shine some X-ray on it, and then maybe look at which angles radiation comes out. This is essentially what is done, but there are some real-world modifications to this technique. So first of all, yes, we have single crystals of stuff like this perfect salt crystal here is a macroscopic crystal. And then what we can do is we can shine X-rays on it and then maybe change the wavelength to see how the diffraction peaks evolve as we change the wavelength. And from this we can deduce not only the crystal structure, but also the spacing between the orientation of this crystal, which way it is rotated in space. And this approach is called the Lauer Method. Turns out to be not very useful in practice. And one of the disadvantages of this approach is that the crystal is fixed at a certain orientation, and you may miss a lot of the interesting planes that are just going at different angles. So then you can modify it by setting up an apparatus where your crystal is constantly rotating and you're observing the spectrum. So we are actually not going to talk about the first two. We are going to focus on this powder method. Powder, because of how most real materials look like, they are not single crystals. They are polycrystalline. So they're made of very small single crystal pieces, which are all stuck together into a solid. But there are pieces which are oriented in random directions. So this monocrystalline piece has this kind of basis, and this one has a different kind of basis, and the third one yet another. And we, in principle, can have all kinds of possibilities in a single piece of material, yet we still want to know something about its crystal structure. Seems like this would be a more useful technique that would address these kind of structures, and this is called this powder method, which we're going to start discussing today. So the way it works is actually rather intuitive. You have an incident beam of X-ray. Here is a sample. And now you have all kinds of little crystals with all orientations possible there. It turns out that there is a relationship between the incident beam and the scattered beam, which is given by the Lauer condition, for example, right? That they're related by a vector g, or they're related by some angle 2 theta. So if the crystallines are all randomly oriented, we are not going to get just one angle 2 theta, but we are going to have a ring. All possible angles around the incident beam from all the little pieces of the polycrystalline material will be allowed. And so X-ray diffraction pattern will look like a set of concentric rings centered around the central beam. This is from the averaging over all, summing up all the possible orientations of the polycrystalline samples. Now, this is another experiment I did myself. So but this one is nice. It gives you instant satisfaction. And so we're going to go through this example. So you have this kind of chamber. It's called Debye chamber. And you have a special photographic film which is sensitive to X-rays, kind of like in your doctor's office. And it has a band shape. So you put this film all around the chamber. You line it up. And then you shine a beam through. You put your sample in the center. And then you develop this film, like they do in your doctor's office. And this is the kind of thing that you might get. So the big holes here and here are where the beam came through. So that's overexposed. Or maybe there is even a hole there on purpose to line them up. And these dark rings here are the diffraction peaks that are given by when the Bragg law is satisfied for some family of planes. So these days you don't put the film there. You just have some kind of a detector which either moves around in a circle or has this kind of shape, and it records all the angles that you want in a digital form. This is a semiconductor detector. It counts the photons. Some kind of an avalanche photodetector, for example, counts the number of photons and tells you for which angles. And this angle is 2 theta if you work out the geometry, the data that you get from Bragg's law. And this angle would be 2 theta then. Okay. So let's look at a specific example. This is what you might see if you do this X-ray diffraction, XRD, on an aluminum crystal, polycrystalline material, aluminum polycrystal. And you will have these peaks. They will have intensities. And you can measure fairly precisely their angular positions. So which angles give you peaks. You can label them A, B, C, D, and so on. And this pattern is obtained for illuminating aluminum with a specific wavelength of X-ray, which we know very well because this is a copper crystal. And we know that it's a certain atomic line in copper, so we know the wavelength to some insane precision of 6 digits. Okay, so this allows us to very precisely relate these angles to positions, to lattice spacing. So this is a recap of what we might expect if we limit ourselves to cubic crystals. So HKL are the Miller indices, and PIF are the notations for the simple cubic, BCC, and FCC. And so these are the Miller index sets. You can see that for the simple cubic, for the P, they're essentially all allowed. There are only absences for some lines here because the lines are arranged on this number n, which is h squared plus k squared plus l squared. Turns out that for the number 7, you cannot come up with a sum of 3 squares that will give you 7. Okay, so there is no set of Miller indices here neither. But for all Miller indices, simple cubic is allowed. Here's another one at 15. You don't have any Miller indices that would give you h squared plus k squared plus l squared 15. And so this one is also absent. So all of them are allowed, but some are noticeably missing. And now for the BCC, the first one's absent, the third one's absent, the fourth one's absent. And if you just write out the numbers n, which are allowed, you will see that they are 2, 4, 6, 8, 10, 12, 14. At least the many first ones are all even. So there are no gaps here. They're all even. Eventually there is a gap, I believe, but not until 14. Okay. Now for the FCC, it's complicated. It's 3, 4, 8, 11, 12, 16. So It is a distinct set that you can calculate, but it's complicated. So there are many missing ones here. So how is this table useful? Well, in the following way. So here is the data for aluminum that we had 2 slides ago with the peak names A, B, C, D, E, F, G, H. And this is the actual data, the angle 2 theta, that you can read off of the XRD data. Now, the next thing you can do is you can calculate using Bragg formula the distances between the planes that would give you these kind of angles. And so the distances are 2 Mach, 2.3 angstroms, 2 angstroms, 1.4, 1.2, 1.1. So they go down as the peaks increase in angle, so you probably correspond to higher and higher Miller indices, right, as we discussed in the beginning. Now if we scale them all by the first one, so we scale them all by the first one, because we don't know if the first one is there or missing, right? So what we can do is scale it by the first one or by the I think by the first one. So and just we have a set of numbers like this, and then okay, for convenience multiplied by 3. This is not the procedure that you have to follow for every set of lines. You just have to look at them and figure out which h squared plus k plus l squared this corresponds to. And so this will be one procedure that they did in this example, but you can see that it corresponds to this pattern 3, 4, 8, 11, 12, 16 if you relate it to this formula. And then actually for this pattern you can see that this must be FCC based on what we had in the previous slide. So the first one would be 3, then 4, then 8. That would be the ratio between these from these angles. Sanity check. All of these should give you the same lattice constant from each of these planes using this formula, plugging in the HKL that you've guessed by this analysis. You should get the same A, and that works out to be pretty accurate, with A equal to 4.05 something angstrom for all of these. So this makes sense. So this is how you deconstruct, calculate D, and then try to match it to a pattern for FCC, BCC, or something else. So obviously, if you're an X-ray crystallographer, you have a lot of experience with this, and just by looking at the pattern, you can say, this is FCC, right? And so now these are labeled for you, 111, 200, 220, 311, and so on. And these are the h plus k plus l squared numbers that correspond to these peaks. So they make a very nice sequence. And we now have determined that aluminum is an FCC crystal. This is how it works. Okay, maybe one last thing for today. Let's try to figure out what this one is. So simple cubic FCC, BCC. Simple cubic, why? It has many, yeah, and there is also another hint that you can see here. Okay, so another hint is that if you look at the spacings of these ones, there is one spacing that is twice as large, and that would correspond to h squared plus k squared plus l squared equal to 7, which is not possible. And so this is noticeably absent here, and this is the 15, which is also absent. So for this material, barium titanate, this is a simple cubic. And indeed, you can tell it from how many there are, and they look very regular. Right? So they're all allowed. 1, 2, 3, 4 are allowed. And even the ones that are not allowed are missing in here. Okay, we'll stop here. We'll pick up on Thursday.